Let's talk about neutralization reactions. Alright, the idea behind this type of reactions is that you are going to be mixing an acid with a base. And we talked about this type of reactions back when we introduced the idea of balancing equations, and we talked about the various types of reactions. We classify them under double displacement, which they technically are. They're double displacement reactions, but now we're going to get specific in terms of what they're doing. And the idea is that with this concept of the conjugate pairs, we can now see what's going on. You are double displacing, sodium and hydrogen. Basically, the H plus is going with the OH minus, the Na plus is going with the Cl minus. But the idea right here is that the molecules that start with the H, those are your acids. And these three in particular are strong acids. They're part of the 11 that I'm asking you to memorize, right? So if you haven't done that by now, definitely start memorizing those strong acids. And over here you have metal hydroxides, metal oxide, metal oxide. So you can actually carry out reactions with them. And in order to predict the products, especially if you don't have hydroxide as the base, you have to go with the knowledge and the concept of the conjugate pairs. Okay, so yes, we're going to be dividing these things. Now, the charges are going to remain constant when you go from left to right side of the equation. So you could look at this from the point of view of a double displacement reaction where you copy everything down in terms of the charges for the cations and then you swap the anions. So for magnesium oxide, you're dealing with magnesium 2 plus. Um, Bromic acid, H is going to be H plus. Aluminum oxide, aluminum is 3 plus. Sulfate is 2 minus. So you can look at the charges to arrive at the conclusions here, right? So you write the cations in the same spot, sodium first, H plus later, and then you swap the order. The chloride now goes with sodium, the hydroxide goes with H plus, and you use the charges to basically come up with the proper proportions. In this case, everything was 1 plus or 1 minus, so you only need a 1 of each. But notice that for H with the OH, you turn that into water, right? Over here, you have magnesium 2 plus that's going to be mixing with bromate, and the H plus once again is mixing with well, technically oxide, but the oxide will turn into hydroxide. So here you will still get water out of this procedure. And because of the charge of magnesium, you're going to end up with two bromates. But this equation is no longer balanced, so now you have two bromates. You have to place a 2 in front of HbRO3 to balance it. And if you look carefully, that gives you two H's and one oxygen, which is indeed water. So this works out in terms of the balancing. Now, aluminum oxide and sulfuric acid, similar idea. Aluminum 3 plus and H plus get combined with the charges. Here I'm actually going the extra mile to show you with the charges that this is going to work out the same way. The 3 has to go in front of sulfate, the 2 has to go in front of aluminum, the 2 has to go in front of H, the 1 has to go in front of oxygen, so you end up with water and aluminum sulfate. And of course you need to balance your equation. You have 3 sulfates, only 1 sulfate here, so you need to multiply sulfuric acid, excuse me, by 3, and that gives you a total of 6 hydrogens. You only have 2 here on the right side, so you need to multiply water by 3. And the moment you do that, everything else looks good. You have 3 oxygens from the water, 3 oxygens in the salt, 2 aluminums, 3 sulfates, 3 sulfates. So this looks great. This is balanced now. All right, so in each one of these cases where you start with hydroxide or oxide in your base, you end up making water. You also produce a salt in the course of the neutralization reactions. All right, now we're going to look at a subdivision of the acid-base reactions, those that actually form gases. We're going to start with sodium bicarbonate, also known as sodium hydrogen carbonate. This particular molecule is the base, and you're mixing it with hydrochloric acid, which is a strong acid. So we would do the same thing. Sodium is the cation, H plus is the other cation, so you would swap hydrogen carbonate and chloride between them. Now the problem with this is that if you do that, you will end up with H2CO3, but H2CO3 is actually unstable. In fact, if you follow the rule that we applied last time, namely that you're going to end up forming water, in that case, you'll say, okay, we can produce sodium chloride because of the exchange, the double displacement, but we'll produce water. And if you look carefully, you say, well, okay, we have accounted for two H's and one oxygen. You have the two H's there, and we have one oxygen, but we had CO3 to begin with, so we only take one oxygen away. What that means is that we must be producing CO2 as well in order for everything to balance out. And indeed, reacting bicarbonate salts or hydrogen carbonate salts with an acid, even a weak acid like acetic acid, will produce CO2 as one of your products. But now you're producing salt, CO2, and water. And this does not need to be necessarily hydrogen carbonate. It could just be regular carbonates. In the case of calcium carbonate, also known as marble, here, if you add a strong acid like perchloric acid, you will end up forming once again, yes, your calcium 2 plus, which will be combining with your perchlorate 1 minus. That's your double displacement. But the moment the H plus mixes with the carbonate 2 minus, that will decompose into water, and yes, you might have guessed it, CO2. And at that point, you have to use the charges of the salts to come up with the proper proportion. Okay, so now what needs to happen is that you need to balance this equation. You have two perchlorates on the right side, you only have one on the left side, so put a 2 in front of perchloric acid. And at that point, you have two H's plus one O to give you water, CO2, everything else is balanced. So hydrogen carbonate and carbonate in combination with an acid will give you water and CO2, so you have to be aware of that. The remaining species will be the salts associated with the cations and anions of the components. All right, another equation to be on the lookout is the ones with ammonium. Ammonium is technically a cation. It doesn't have any lone pairs on nitrogen, so it cannot behave as a base. The only thing it can do is behave as an acid. So if you react ammonium salts, in this case ammonium bromide, with a strong base like potassium hydroxide, ammonium gets exchanged, the bromide and the hydroxide get exchanged, right? In particular, the bromide will go with potassium, the hydroxide will go with ammonium. But this time around, instead of just forming ammonium hydroxide, what you form is water and NH3. And NH3 is one of the gases, right? So CO2 is a gas, NH3 is a gas. This is some of the equations that will lead to formation of gases. And they are, in essence, regular acid-base reactions, but you need to be aware of this. So if I give you an equation where I'm mixing hydrogen carbonate with HCl or any other acid, you better give me CO2 as your product. All right. Now, there are acid-base reactions, technically speaking, that are actually single displacement reactions, and we've sort of touched upon this stuff in the past. But the idea here is that you can form gases by treating a neutral metal, like lithium, magnesium, or scandium, with a strong acid. And when you do that, because the lone species is a metal, you will displace the cation. And in this case, the cation is H+. So displacement of the H plus cation will give you a salt, sure. In this case, it will be lithium chloride or magnesium bromide or scandium chloride. But you will produce hydrogen gas, right? Because the H is going to be displaced by the metal. And the one thing you have to remember is that H plus turning into neutral hydrogen is going to be H2, right? So this is the elemental form of hydrogen. So you have to write that, and you also have to balance the equation. So you put a 2 in front of HCl because you have to have two H's in H2. That means that you have now two chlorides, so now you have to put a 2 in front of lithium chloride. But then that changes the amount of lithium by 2, so you have to put a 2 in front of lithium. So, that kind of like complicates the story a little bit, but you have to balance it. And not only that, but you have to remember that hydrogen in its elemental form is one of the Hofbrinkel gases. Same idea with magnesium bromide. You will end up with MgBr2 because of the 2 plus charge of magnesium and the 1 minus charge of bromide, but you will be producing H2 as well. Okay, so you have two hydrogens, you need to put a 2 in front of HBr, that gives you two bromides, and you have two bromides, one magnesium, so that's balanced as of now. With scandium, here you will have to know that the charge of scandium is 3 plus because it's in group 3. And so mixing that with Cl minus will give you 1 scandium and 3 Cls, and you will still form H2. So we're going to have to put a 2 in front of HCl. However, that will only give us 2 chlorides in the formula, and we actually have 3. So actually, we're going to have to double the amounts of everything. In fact, let's multiply the scandium chloride by 2 to end up with 6 chlorides. That tells you that now your HCl needs to be multiplied by 6. Yes, and the scandium needs to be multiplied by 2. But now that tells you that, okay, you have to have 6 hydrogens, which means that you multiply the H2 by 3. So even though up until that point it looked like you could reduce this by dividing everything by 2, the moment you get the coefficient for H2, you realize actually you can't. These are the lowest ratio coefficients for everything in the equation. But long story short, via double displacement of an acid upon reaction with a neutral metal, which is higher on the activity series than hydrogen, will lead to formation of hydrogen itself. Alright, so in the next video, we'll start talking about titration. So I'll see you then.